Good morning. Today we're going to talk about section 4.5 entitled Multiplication Rule, Complements, and Conditional Probability. Alright, the 4.4, which we've just finished, was multiplication rule, the basics, and we're going to extend the concept of multiplication rule to handle, well, a couple of major topics in this section. We're going to talk here about at least one type probabilities, the probability of at least one characteristic of interest among certain trials. Also, our second major topic in this section is going to be conditional probabilities. Well, conditional probabilities are computed assuming a given condition has occurred. And we'll talk more about that later. The first thing we're going to talk about today is the at least one probability scenarios. Alright, I always like to try to motivate things with an example. Motivation example, let's see, again, let's do a boy-girl thing. Assume boys and girls are equally likely in any birth, and I'll say a couple has 3 children. Okay? And I'll say find the probability of at least one boy in those 3 births. So again, the big clue here is at least one. That's one of the major topics of today's online class. Alright, how are we going to figure this out? Well, of course, we could brute force list the sample space. That may be cumbersome. With 3 children, it's not too bad. 3 children, let's see, we got boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. Like we've done several times in this class, list the sample space for 3 children, allowing any child to be of any gender and in any order, right? Alright, I want the probability of at least one boy in all these outcomes. At least one boy, okay? Well, clearly we've got 8 possible outcomes, gender-wise, and having 3 children. And how many of these outcomes have at least one boy? Well, I think we can see that, well, let me list them here. At least one boy, there's one, there's one, there's one, there's one. Let's see. 7 out of 8 outcomes have at least one boy. So my final answer is going to be 7/8, or in decimal, 0.875. Now, of course, we're not going to be brute force drawing up sample spaces all the time. That may be an entirely too cumbersome manner, as we saw in the last exam. Let me cite to you another way, or suggest to you another way. Only one of these outcomes has no boys. I think we can see it there, at the bottom of the list. Only one of these outcomes has no boys. I'm going to write my probability this way. I'm going to claim these events are complementary. At least one boy and no boys. Please convince yourself that these 2 events are complementary events. Okay? Alright, well then I can say the probability of at least one boy is 1 minus the probability of no boys. You agree? Because they are complementary events. Well, the probability of no boys is equivalent to the probability of all 3 being girls. Think you'll agree? And what's the probability of that all 3 are girls? Well, that's going to be 1/8, right? So I can simplify this a bit and say this is 1 minus the probability of all 3 girls is 1/8, and 1 minus 1/8 is, of course, 7/8. So we get the same answer without drawing up a cumbersome list of my entire sample space. I'll call that 0.875. All right, I'm going to extend this example to the idea of the general idea of at least one, really of any characteristic of interest. Let me write this down. In general, the probability of at least one in any given scenario is going to be 1 minus the probability of none, whether you're talking about births or deaths or high blood pressure or number of boys, whatever. Okay? The probability of at least one is 1 minus the probability of none. All right, I'm going to embrace this model, and I want to work out example 1 in our text, and it's on page 169. Let me read it to you. You'd probably want to turn there yourself, page 169. All right, they want the probability of at least one defective DVD. All right, let's read the scenario here. Topford Development supplies DVDs in lots of 50, and they have a reported defect rate of 0.5%. So the probability of an individual disc being defective is 0.005. Let me write that down. The probability that one disc is defective is 0.005. It follows that the probability of a disk being good is 0.995. All right, so the probability that one is good, that's a G there. The probability that one is good, well, it's going to be 1 minus the probability that one is defective, and that's 1 minus 0.005, and of course that's 0.995. Okay? If a quality control engineer wants to carefully analyze a defective disk, what is the probability of her getting at least one defective disk in a lot of 50? All right, so the probability of at least one defective in 50, a lot of 50, well, by the above example, it's 1 minus the probability that none are defective in the lot of 50. Okay? Well, how can I simplify this? This also is equal to 1 minus, well, the probability that none are defective is equivalent to the probability that all are good. If none are defective, all 50 of them are good. All right, now I'm going to get a value for the probability that all are good by the multiplication rule, right? The probability that one is good is 0.995. Well, the probability that all 50 are good is going to be 0.995 raised to the 50th power. Okay, by the multiplication rule, this is the probability that the first one is good times the probability that the second one is good times the probability the third one is good, dot, 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 all the way up to the probability that the 50th is good. And we can summarize that in this nice, concise fashion. The probability that all 50 are good is 0.995 to the 50th power. So if I grind this out on my calculator, well, I have to do 1 minus 0.995 caret 50. That'll do it nicely on your TI calculator. And I get 0.222, we'll call it. Alright, so in a nice concise way, without writing a sample space that's 2 to the 50th power units long, we can get a nice concise answer embracing that above example. The probability of at least one is 1 minus the probability of none. Let's do another one like this. Number 10 on page 172. I believe this one's in your homework list. Number 10 on page 172. Let me turn there and read the problem. Let's see, 10. At least one working calculator. A statistics student plans to use a TI-84 calculator on her final exam. From past experience, she estimates there is a 0.92 probability that the calculator will work on any given day. Alright, so the probability that one calculator works, I'll say G works, or it's good. The probability that one is good is 0.92. It tells us that explicitly in the problem, right? Because the final exam is so important, she plans to use redundancy by bringing in 2 calculators. Okay. What is the probability that she will be able to complete her exam with a working calculator? Well, we're really looking for this. We really want the probability that at least one in those 2 calculators is good. All right, if that event occurs, she will be successfully able to complete her exam. All right. By our model, remember, let me write it out in general, the probability of at least one is 1 minus the probability of none, always, no matter what the scenario is. Well, the probability of at least one good in this situation is going to be 1 minus the probability that both are bad. Well, let me write it down here. I'll say it's none good, right? The probability of at least one good is 1 minus the probability of none good. Okay? Alright, I claim that's, well, the probability that none is good, that's 1 minus the probability that both are bad. If none are good, that means both of the calculators are defective or bad. And again, I'll invoke the multiplication rule. The probability that both are both are bad, well, it's the probability that the first is bad times the probability that the second is bad. Well, the probability that the first one is bad is 0.08 times the probability that the second is bad. Well, that's also 0.08, so I'll equivalently just raise that 0.08 to the second power. Alright, so again, learn to recognize this pattern. It's 1 minus something to the something power pretty much in all these at least one problems, and 1 minus 0.08 squared is 0.9936. So we can see she does get an advantage in probability here by bringing in 2 calculators. If we look up here, the probability that one calculator is good is 0.92. The probability that at least one is good is slightly higher, at 0.9936. Pretty good chances that at least one is going to work given that information. Okay? That's number 10 and page 172. Let's see. Let's look at number 9 on page 172. Let me get a fresh screen here. Alright, this is number 9. Also in your homework list on page 172. Let's read the problem. If you make random guesses for 10 multiple choice test questions, each with 5 possible answers, what is the probability of getting at least one correct? So we've got a 10-question quiz, multiple choice quiz, and there's 5 choices per question. What is the probability of getting at least one correct? All right, it's assuming random guesses on all the questions. Okay, let me write that down. If random guesses are made, find the probability that you get at least one correct. And I'll abbreviate it like so. And again, remember our model, the probability of at least one is 1 minus the probability of none. Okay? I'll invoke that here. The probability of at least one correct question is 1 minus the probability of none correct in those 10 questions. Alright, well, what's the probability that none are correct? Well, that's 1 minus the probability that they're all 10 are wrong, right? I can rephrase it like that if I wish. And I'll invoke the multiplication rule here. Well, the probability that 1 is wrong is going to be 4 out of 5, right? 4/5. You've got 5 choices per question. Only 1 is correct. So the probability that 1 is wrong, any one question is wrong, is 4/5. And by the multiplication rule, the probability that 10 are wrong is going to be 4/5 to the 10th power. And the probability of at least one correct is going to be 1 minus 4/5 to the 10th power. Alright, I can punch this out on calculator. Well, of course, 4/5 is 0.8. I can call that 1 minus 0.8 to the 10th power. And punching it out on my calculator, I get a probability of 0.893. So the probability of at least one correct in 10, assuming random choices are made, is going to be 0.893, or a pretty strong probability. Of course, getting one correct, or at least one correct, probably is not a good thing to plan for. Alright, that's number 9 on page 172. I'm going to do one more of these at least one type problems. This is also on your homework list. I hate to ruin the surprise on your homework assignment. This is number 32 on page 174. And let me read it to you. Let's see. 32. Composite water samples. The Fairfield County Department tests water for contamination due to the presence of E. coli. To reduce laboratory costs, water samples from 5 public swimming areas are combined for one test, and further testing is done only if the combined sample tests positive. Based on past results, there is a 0.005 probability of finding E. coli bacteria in any given public swimming area. Alright, so let me write that down. The probability of finding one swimming pool with E. coli is 0.005. Right? The probability that any randomly selected swimming pool has E. coli is 0.005. Okay? Find the probability that a combined sample from 5 public swimming areas will reveal the presence of E. coli. Well, we will reveal the presence of E. coli in this combined sample of if at least one in these 5 pools has E. coli. And I'll abbreviate it like that. Alright, by our model, we should be comfortable with by now, that's going to be 1 minus the probability that none of the 5 pools have E. coli. Okay? Well, how can I describe this? If none of them have E. coli, that means all 5 don't have E. coli. Let me rewrite it like this. It's going to be 1 minus the probability that all 5 have no E. coli, right? Well, if the probability that 1 has E. coli is 0.005, the probability that 1 has no E. coli is going to be 1 minus that, or 0.995. Alright, so the probability that all 5 pools don't have E. coli is going to be that 0.995, the probability that any pool does not have E. coli raised to the 5th power by the multiplication rule. Okay. I can punch this out, 1 minus 0.995 to the 5th power, and I get 0.0248. So the probability in this sample of 5 pools that at least one of them has E. coli is going to be 0.0248. Alright. The book asks a critical thinking type question: is that probability low enough so that further testing of the individual samples is rarely necessary? Well, remember from the problem description that we will further test this combined sample if at least one turns out has E. coli. Right? And that happens with about a 2% chance. So this says, I summarize it like this, I'll say about 2% of the combined samples will be tested further. And that looks like a fairly low rate for the further study. And I suppose that ends this problem. Okay? Alright, so we've done 4 examples of at least one type scenarios. There's some written up in the book as well. I want to move on now to conditional probability as our second major topic in this class. Conditional probability. And what is conditional probability? Well, typically we write conditional probability with this syntax. We read this vertical bar as the word given. So what we're really doing with conditional probabilities is assuming a prior condition has occurred. So this is the probability of B, event B, given event A has already occurred. And we read it just like we see it here, the probability of B given A. I want to cite to you the chapter problem matrix again. You'll recall this, of course. We've got pre-employment drug screening subjects. Some of them did drugs, some of them did not do drugs. Some of them were caught by the machine, some were not caught by the machine, and with the resulting numbers. Same matrix we've used several times in this chapter already. Alright, I'm going to ask us now about some conditional probabilities. What's the probability? Well, again, we'll randomly select one subject from these 1,000 subjects, right? Remember the grand sum was 1,000 here. What's the probability of finding a positive test result given a drug user was chosen? Alright, what's the probability of positive given drug use? Alright, so what we're going to do, we're going to assume a drug user was chosen. And we've got 50 drug users in this sample. Alright, within that restricted pool, how many of them received a positive test? Well, clearly 44 out of those 50 had a positive test. And if I simplify that to a decimal, it's 0.88. Similarly, let's try to reverse those events. Something should come to light here. What's the probability of finding, again, we're randomly selecting 1 on all these examples. What's the probability of randomly selecting a drug user given it was a positive test? Well, how many positive tests do we have here? Looks like the sum of that positive test column is 134. So assuming that positive test has already occurred, what's the probability of picking a drug user? Well, of course, that's 44 over 134, and I can punch that out to 0.328. Notice these numbers are not the same. That shows that this conditional probability is not commutative. Right? The probability of A given B is not necessarily equal to the probability of A given B. Okay? Let's try another one here. Again, I want to work with the same table here. Give me a second to erase this. I might as well just rewrite the table. Hang on. Give me a second. We've got drug users, no drug users, positive result, negative result. That's the familiar values given in this study of 1,000 subjects. Alright, I believe these two are from your homework assignment. What's the probability of again, we're randomly selecting 1. Let me write that down. We randomly select 1 from this pool, and I ask what's the probability of finding a negative result given. Remember to read this, it's not a quotient bar, it's a symbol. All right? Symbol arbitrarily described as, we read as the word given. What's the probability of negative given drug user? Well, how many drug users do we have? We've got 50 drug users. So we're really restricting our sample space to the 50 drug users. And how many of those have a negative result? 6 of those drug users had negative machine results, and 6 over 50, of course, reduces to 0.12. Similarly, what's the probability of positive result given no drug use? Well, again, we read this bar, this vertical bar, as given, assuming no drug user has been chosen. So we've got, let's see, 950 no drug users, and out of that pool of 950, 90 of them received a positive test. So this probability is 90 over 950. I'd call it 0.0947. Alright, so that well covers our two major topics of the day, at least one, scenarios, and conditional probabilities. Alright, we're getting towards 29 minutes, so we'll call it a day. This concludes section 4.5, complements and conditional probability.